Zoe's and Michelle's Math Hour!
Hello everybody! Last time on Zoe and Michelle's Math Hour we proved the derivatives of inverse trigonometric functions. Today we are going to work through some examples of these derivatives to shed some light on how to use them. Michelle, can we possibly solve some equations using these formulae?
So now we're going to solve the example of inverse sine trigonometric function derivative. And since there's x squared, we'll have to use u sub. And if we do the exact same thing that we did when we're proving, and we have to use, obviously, trigonometric identities here too. So we get cosine y equals to square root of 1 minus sine squared y. And since sine y is u, we can substitute that as square root of 1 minus u squared. But in here, since we have to get dy dx at the end, we have to find du also. And that gives us that du dx is 2x. So we could multiply dy du, which is 1 over square root of 1 minus u squared, by du dx to get dy dx, which will give us 1 over square root of 1 minus u squared times du dx that we got, which is 2x, which is going to be 1 over 1 minus x to the 4 times 2x. Now we're going to solve the example of inverse cosine derivative. And in here, also, we have x over 3, which is a bit complicated than what we did when we were proving. So we're going to use u sub again, and we're going to let u to be x over 3. And we know that that equation is the same thing as cosine y equals to u. And so we're going to get the derivative of that whole equation with respect to y. And now we're going to use inverse trigonometric identities again. And that gives us that. So we can substitute that, the equation. And since we know that cosine y is u, we can say that it's negative root of 1 minus u squared, and the same thing as what we did when we were proving the thing. We're going to multiply du dx to du dy to get dy dx, which gives us negative 1 over square root of 1 minus u squared times 1 over 3. And we're going to put the x over 3 into the u place again. So we're going to solve an example of inverse tangent derivative. And in here we also have x over 5 and a coefficient in the front, so it's going to be a bit complicated than other examples. So we're going to use u sub again, and the 6 at the end is going to be cancelled out
because the derivative of 6 equals 0.
Yeah. And so we're going to put 1 over 5 this side, and we're just going to figure out what inverse tangent of x over 5 derivative would be first. So we obviously are gonna take the derivative of it with respect to y, and when we use trigonometric identity there, secant square y equals to tangent square y plus 1. And we know that u equals to tangent y, so that's going to be u squared plus 1. And dy du, which is flipped over, is going to be 1 over u squared plus 1. So when we want to get dy dx, we're going to multiply by du dx. And we know that u is equal to x over 5, so du dx would be 5 over 1. 1 over 5.
1 over 5.
Yeah. So we're going to multiply that by that equation and substitute, plug the x equation again, the u place, which is going to be x over 5 squared plus 1. And then since that's the value of derivative of inverse tangent x over 5, we're going to multiply it by 1 over 5 again because we had it before we were solving the derivative first. And that gives us 1 over 25 times 1 over
X over 5 squared plus 1.
yeah.
Now we're going to do a derivative of the inverse of cotangent.
And we're also going to use u sub in this case too. And we know that cotangent y equals to u. And when we get du dy by taking derivatives of both sides with respect to y, and if we use trigonometric identity here, we know that negative cosecant square equals to negative 1 minus cotangent square y, which is going to be negative 1 minus u squared. So in order to get dy du, we just flip it. That's going to give us negative 1 over 1 plus u squared. Now to get dy dx, we also have to multiply it by du dx. So we have to get du dx first, which is going to be 5. So now all we need to do is plug in the u equation in form of x and multiply it by du dx, which is going to be 5. That gives us negative 5 over 1 plus 5x squared. We have the answer there. Now we're going to solve example of inverse secant derivative problem. And we're also going to use u sub because it has a complicated equation in it. And we're going to take derivative with respect to y. That gives us secant y times tangent y. We know that tangent square y equals to secant square y minus 1. And so we can know that tangent y equals to square root of secant square y minus 1. And we're going to plug in that to tangent place there. So it's going to be secant y times the whole chunk that we just got by trigonometric identity. And we know that secant y is u, so we're going to use u sub there. And we're going to flip it over to get dy du. And to get dy dx, we're going to have to multiply it by du dx.
Now we have to find du.
So
Du dx, sorry.
u equals to x squared minus x, which is going to give us du equals to 2x minus 1 dx. So du dx would be 2x minus 1. And we know that dy du is 1 over u times u square root of u squared minus 1. and then we're gonna multiply it by du dx, and we're just simply gonna put x squared minus x into u again. And that's gonna give us the answer. Lastly, we're gonna solve example of inverse cosecant derivative. And since we have 5x here, we're gonna let u to be 5x. We know that y equals to inverse cosecant u is the same thing as u equals inverse cosecant y. So we're going to take derivative of it, and we know that cotangent y square equals to cosecant square y minus 1, and that's going to give us cotangent y is square root of cosecant square y minus 1.
So multiply negative cosecant y times that whole chunk that we just got.
Yeah. And then we're going to put u in it. And here, in this case, cosecant y would be the u. And we're going to flip it over to get dy du. It's just flipping du dy to dy du, so you get the reciprocal of it. And then we're going to multiply by du dx to get dy dx, which is going to be 5. And so we know that it's going to be negative 5 over u times u square root of u squared minus 1. And we're just going to put 5x in the u place because we let u to be 5x the first time.
That was great, but could we maybe have an example to see how we can apply this to the real world?
Sure.
Alright, the problem states that a photographer is taking a picture of a 4-foot painting hung in an art gallery. The camera lens is 1 foot below the lower edge of the painting. How far should the camera be from the painting to maximize the angle subtended by the camera lens?
We want to maximize the angle of it, and we want to get the distance of the camera from the picture where it maximizes the angle. So we're going to set x for the distance because we want to get distance for the answer. Now we have the picture on the side, and we're going to let angle B be the angle that is being maximized. We're gonna say that we know that angle B equals to theta, angle theta minus angle A. And we're gonna draw a triangle. We're gonna draw a triangle to make sure we understand this. So when we draw the bigger part of triangle, we know that tangent theta would be 5 over x. And that means inverse tangent of 5 over x means theta. So we are flipping it, but it's basically the same thing that we did when we were proving. And we're going to draw a small portion of the triangle now, and we know that the height of it is 1 feet. So tangent A is going to be 1 over x. And that means it's the same thing as inverse tangent 1 over x equals to A. And so when we substitute those measurements, those equations in theta and A, it's gonna be in that minus that. And so we know that theta minus A, which is also B, is going to be inverse tangent of 5 over x minus inverse tangent of 1 over x. So now we're going to take derivative of this function since the candidates for critical number are existing where the derivative equals to 0, and we want to find the maximized value of angle B, so we're going to take derivative of it.
But hold on, first we're going to change it to cotangent, correct?
Yeah, because if you use inverse tangent, it gets complicated.
It turns into a logarithm.
Yeah, so it'll be way easier to solve it by changing it to cotangent there.
So you would just flip what's inside the tangent from 5 over x to x over 5, and from 1 over x to x. So that's how you do cotangent.
Because cotangent and tangent are
flippable.
Yeah, reciprocal.
Yeah.
They're in reciprocal relation.
Now we're doing u sub for cotangent.
Yeah. And now we have du dy equals to negative cosecant square y.
Because we took the derivative of cotangent y.
Mm-hmm. And
using our trig identities.
Yeah. Cosecant square y plus equals to cotangent square y plus 1. So we can say that equals to negative cotangent square y minus 1. And we're going to flip this over to make dy du. But before that, we're going to use u substitute. And in this case, u is going to be cotangent y.
Yeah.
So we're going to flip it now. And that's going to be negative 1 over u squared plus 1. And to get dy dx, we must multiply it by du dx, and so we have to get du dx here. Since u equals to 1 over 5x, du dx is going to be 1 over 5. So the whole thing, which equals to dy dx, is going to be negative 1 over 5 times u squared plus 1. And we're going to substitute, we're going to plug x over 5 to u back. Now we're going to solve the derivative of inverse cotangent x. We're just solving each derivative at one time.
We're splitting the equation into chunks. So first it was cotangent of x over 5, inverse cotangent of x over 5.
Yeah.
And now we're doing inverse cotangent of x, just to make it a little bit easier.
Mm-hmm. So we're basically doing the same thing. And we took the derivative of it, but in this case, since it's x and it's not complicated, we actually don't need to use u sub here. So using our trigonometric identities, cosecant square y equals to 1 plus cotangent square y, and it gives us that is equal to 1 plus x squared. So the derivative of it, which is dy dx, would be negative 1 over 1 plus x squared. So now we're going to use these values to solve the whole equation. And it's very simple. Once we got each derivative, and so we're just simply going to subtract one from another. And since the derivative of inverse cotangent x was a negative function,
when you subtract a negative, it's a
Yeah.
positive, so we're adding the 2. Well, we're subtracting the 2.
and we're just gonna make it to one polynomial function so that we can see which one makes the denominator 0
Yeah.
or numerator.
Right, because we're trying to find
Yeah.
the maximum, the points where there could be a maximum. So
The
we have to find where
candidates-
it's 0.
The candidates exist where the function equals to 0 or where it doesn't exist. But in this case, what's the bottom?
The denominator.
Yeah, the denominator can't be 0 since it has x squared plus something. We have to find the critical point where it makes the derivative function equals to 0. As I mentioned, the candidate for derivative is gonna be where the numerator equals to 0.
Or it does not exist.
Yeah, but in this case it has.
But it always
Yeah.
exists because the denominator
has x squared
x,
plus
yeah.
1 or plus something positive.
So using a calculator, we found that x equals plus or minus the square root of 5 was the x answers for f of x equals 0.
However, in this case, since x is a distance, it cannot be a negative thing.
So that means that the answer must be the square root of 5.
Now you can probably solve any problem including derivatives of inverse trigonometric functions on the AP test. These are really helpful when trying to remember your trigonometry too. So you could do them for fun. Just remember your trigonometry and your derivative formulae of the inverses and you'll be fine. Until next time, goodbye.
Goodbye.